Hi and welcome to this webinar about printed electronics. My name is Joanne and I'm today's host. With me this afternoon is Dr. Zachary James Davis, who will present the webinar.
All right, thank you, Joanne, for a nice introduction, and thank you everybody for participating in our webinar today. The webinar title is Printed Electronics and Nanomaterials for Printed Electronics. My name is Zachary James Davis. I have a PhD in Applied Physics from the Technical University of Denmark. Right now I'm a team manager at the Danish Technological Institute, leading a group working with the nanomaterials and printed electronics. So just a little bit about what we're going to talk about today in the webinar. First, I'm going to describe some application areas and give some examples from commercial available products to what's the future of printed electronics as I see it. Then I'm going to go more detailed into printing versus lithography for the production of electronics, sort of give you the advantages and disadvantages of these techniques and when you should use printing, when you shouldn't. Then I'm going to go into some technical issues about the different printing technologies and sintering technologies. And then I'm going to go more in details with nanomaterials. So what is the role of nanomaterials in printed electronics, and what are the opportunities and the challenges of that? Finally, when we're done with all the sort of the nice things about printed electronics, I'll talk about what we are doing here at DTI and how we can help you with your ideas within the field of printed electronics. So the first thing I want to talk about is the application areas for printed electronics. Of course, so actually there's a lot of fields and a lot of applications that are actually already using and can use printed electronics. The biggest sector, the biggest market using printed electronics right now is actually the photovoltaic market. Most, if not all, of the solar cells that you see have actually printed silver electrodes, bus bars we call them, on top of them. So all these are using a screen print technology for printing. On top of that, there is a lot of different things. So if you look on the bottom left-hand side, the retail industry is using printed antennas for smart labels and RFID tags and NFC tags. All of these things are becoming more and more printed. Traditionally, they've been using etch technologies, but now they're actually, I think, at least to 20 to 30% of the tags and antennas you see on the market are actually printed. Wearables is a very up and coming and very exciting application area. So trying to integrate electronics into wearables and textiles. The automotive industry is extremely important. Actually, there's a lot of money going into trying to put more functionalities into automobiles, more sensors, more actuators, more lighting, etc., etc. But at the same time, you don't want to, add added weight, and you want to make it more, they have to be lightweight and as flexible as possible. So printed electronics is enabling the production of flexible, lightweight electronics and sensors inside automobiles. Another application area is energy systems, so not just the fuel cells, the solar cells, but also, for example, there's people printing batteries, so you can actually get flexible and printed batteries nowadays. And finally, printed displays, so going into how to print flexible, you want to put these on flexible, then you can also start to print them. And the last thing is, of course, medical. So EKG electrodes, thermometers, sensors for medical applications is also an up-and-coming application area. Just to show you a little bit of how it's done today. So actually, there's a lot of so these most of the commercial available printed electronics is done using a roll-to-roll or a sheet-to-sheet production. This is just showing some examples of that. This is from CPI in the UK, which we have a collaboration with, which is showing some of the large roll-to-roll production. So in this case, you have a paper or plastic, and it rolls, and then it gets printed on a printing station, and then you do some curing, etc., etc. So this is a very fast and very efficient way to produce printed electronics. This is being used today for a large variety of products, RFID tags, NFC tags, I've talked about, electrodes, ECG electrodes for medical applications, PV electrodes, these busbar electrodes, capacitive sensors in electronics. For example, the sort of the capacitive of these buttons you have on your appliances at home. These are actually, a lot of these are printed and then installed inside the machines. So there's a lot of actual components that are already being produced using printed electronics. Some things that I think are very interesting is the wearable market. Wearables, trying to integrate into textiles and to clothing. And I would say the most, of course, there's some very, very relevant things, for example, medical or health monitoring. So trying to embed sensors inside your clothing that you can wear all the day, and then that can sort of monitor your health, and then wirelessly transmit that to docking stations so if there's something wrong, it just sort of alerts you before, maybe, or even alerts the doctor or the ambulance if something goes wrong. Omatex is a Danish SME, which is actually working quite a lot in this area. So they are developing a lot of these novel technologies for both medical applications, but also for muscle monitoring systems. So the muscle monitoring system they are working on is actually a product or a project they're working with the the European Space Agency, so trying to monitor the muscles of astronauts that are in low gravity environments over extended times. This is something they've been working on for many, many years actually, and actually have a almost a validated product on the market now. Now they're trying to transfer that into some sort of system that can be used for athletes, so to be able to monitor both the activity of the muscles, the oxygen content, etc. So there's a lot of really interesting applications coming up within this field. Last but not least, I will show you a little bit example of a flexible and stretchable battery application. This is the one you see on the right-hand side. This is from the UC San Diego. So the idea is that, of course, you're going to need for all of these applications, you're going to, of course, need some power. So and one way to do it is actually just print a battery inside as well. So a thin layer battery, and that is, of course, if you want to put it in textiles, it needs to be flexible and stretchable. The last thing I want to show in applications is a little bit more of what I see the future. So the idea of what I've been showing so far, most of the products, at least the commercial products, are based on 2D electronics. So it's single layers or maybe 2 or 3 layers of patterning electronics. So I think what we're going to see in the future is actually true 3-dimensional electronics. So this is a nice example. This is actually, so just by using 2 inkjet heads, in this case one is containing a conductive ink, the other is taking a polymeric ink or a non-conducting ink, and then by doing layer by layer deposition followed by UV curing, you can build up sort of 3D structures which have embedded electronics. So there's a lot of examples. For example, in the A, there's just some electrodes that are on top of each other, so wires on top of wires and connecting different electrodes. In the C, you see actually an embedded some electronics with a LED inside of a letter. D, you see some sort of helix tracks, which is sort of going like inside a polymer setting, and then on E, you actually see a full functional micro robot with embedded strain sensor and tracks and little wheels and everything. So it's getting more and more complex, and I think this is actually sort of a nice example of a fundamental product or components that can start to become more and more complex by adding, for example, not just 2 materials, maybe 3, 4, 5 materials. Then you can actually really start to add the complexity and actually build true 3D products in the future. So after we go on, so now let's talk shift gears and talk more about into the technology of printing versus lithography. So first, the printing process is quite straightforward. You have a rigid or flexible substrate. You deposit or print whatever material on that substrate, and usually when you after the printing, because the printing is an ink or a paste, it is usually in a wet state. So then you have to do something in order to get it into its correct state, the functional state. And in that case, you have to do a curing or sintering step, which then evaporates any solvents, and then maybe also sinters or melts the pigment or the particles, whatever is in the ink, together to make the conductive ink, the conductive track, for example. If you look at the lithography process, it's a little bit different. In this case, you start with a substrate, and then you deposit on the whole substrate your functional film, for example, electrical metal, and you could do that using evaporation, sputtering, electroplating, etc. So this is very normal. Then you deposit a photopolymer on top of that, and that photopolymer then you have to do through a mask. You expose it and you develop it, sort of like a picture and a camera, and then you use that mask as an etch mask for etching away the metallic layer underneath, and then finally you remove the photopolymer, and then you have your conductive track. So just a little bit about, if we look at these two products or processes and sort of the advantages and disadvantages of each. I mean, printing seems, it is very simple. It's, you print directly what you have. You have an annealing curing step, and you have your features on your substrate. I would say for small and medium scale, and depending, of course, on it's cheap. The tooling for the printing can be very, very cheap, and the actual production is quite straightforward. So in that case, also as well cheap. Features down to 10 micrometers are very are obtainable using depending on, of course, the printing technology. I'll talk about that later, but depending on how much investment you have, but you can get down to at least 10 micrometers. And last but not least is an additive process. That means you're only putting down the materials where you want them. Lithography, on the other hand, is a little bit more complex. You have at least double the amount of steps because you have this lithography step and you have an etching process. In that case, for small scale things, it's actually a little bit more expensive. It's not cheap. But of course, it is, if you want to go on to large volumes, it can become cost effective. And this is what we see in the industry. So, usually this type of etching technique is used for if you have to produce, millions or billions of components, and then it's, of course, very cost effective. The other advantage with lithography is, depending on, of course, on a standard UV lithography process can go down to easily 1 micrometer, if not lower, and with the more exotic or more expensive lithography systems, you can go down to much farther down to maybe tens of nanometers. And this is, of course, what's being used in silicon technology today for producing microchips or microelectronics. It is a subtractive technology. That means that when you're doing, there is actually quite a lot of waste. So all the metal, you're metallizing, depositing metal on the solid substrate and then etching it away. So all that etched metal, unless you can reuse it, is actually lost. So that can become a quite costly production step, depending on the application, of course. So what's enabling printing then? There are some advantages, but of course, the production of today is based mostly on etching or lithography because of the easy feature sizes and the easy scale up. But so that means in order to become, to have printing, to be able to print and make that cost effective, you need enabling technologies. So the first thing you need is a high speed and low cost printing technologies. You also need high-speed curing and sintering technologies, because if you want to produce large volumes, this has to be quick as well. And then what I think is very, very important is actually you need nanomaterials that actually support, that can be printed and that can be cured quickly, and that also gives you the functionality. So if, depending if you want a dielectric material, a conducting material, a semiconducting material, or a sensing material, this is all going to be boiled down to which nanomaterials you can develop and you can formulate in an ink or a paste. So this is extremely important. This is also where there's a lot of development and a lot of research being conducted today, is in this finding novel nanomaterials and getting them into inks that can be printed. So a little bit about the tooling, of course. So if you look at the tooling, just to sort of reiterate what I've just said before, If you look at the tooling cost, if you want to do high throughput, low feature sizes, then you need a UV or a standard lithography system. In that case, you can go from you can do things from 10 micrometers down to nanometers in feature sizes. But of course, this type of tooling is not cheap. It's very, very expensive actually. So it is usually only used for large companies and also large sort of production of components, electrical components. Screen or printing technologies are, on the other hand, quite very cheap in infrastructure, cheap in pricing, but of course they have that sort of disadvantage that the feature sizes, depending on the printing technology, can be limited. Then a little bit about the printing technology, so you sort of see. I actually wrote them in the last slide. So I want to describe 3 printing technologies that are being used quite a lot today. I would say the first one, and actually the most used one, I would say, is the screen print technology. This is the one that's been used for example, printing these electrodes on solar cells. So the idea is you have a screen, and on the screen you put your pattern. You can see an example in the image there. So the screen is a fine mesh of a wire mesh, and then of course you put some sort of polymer on it, and then you develop that polymer to have some openings, and that's where. So then you pour your ink on top of the mesh, and then you swipe it. You sort of squeegee it, the ink across it, and then it sort of deposits through the openings in the mesh, and then it gets transferred to the underlying substrate. It's an analog process. It's a medium to high throughput. You can actually put this screen printing on roll to roll or sheet to sheet lines. This is done quite regularly. You typically get thick layers on the orders of micrometers to tens of micrometers, but of course, as I said, it is one of the more used technologies for printing of electronics. Solar cells, EKG electrodes, a lot of examples of this type of technology being used in industrial settings. Flexographic technology is a lot different. In this case, you have a printing cylinder with a flexible printing plate. This has your pattern on it. Then you're transferring ink to that using an analog roller, and then that ink is then transferred to the substrate. This is also an analog because you need to make your printing plate, of course. This is usually used for high speed, high volume applications. For example, RFID tags where you want a lot of components, smaller components, for example. And also there are, but of course you can use it for other things. There are people using it for solar cells and other things. But I would say the high volume applications like tags, and this is actually usually produced using a flexographic etching printing technique. The last but not least is the sort of the inkjet, and this I put this on there because it's used very often. I mean, in industrial settings, inkjet is not used. It's more for research and development. However, what I see is it is the future of printed electronics, and mainly because it is a digital production technology. That means you actually just have to draw your CAD drawing, your schematics, and then you read it into the printer, and it starts to print. And it's exactly the way you think. It's just like the way, I mean, it's very, very similar to what you have at home. You have the printer, and then you just push print, and it starts to print. However, of course, an industrial printing inkjet printer is a little bit different than your printer at home. You have a lot more print heads in order to become much faster. So you need to, if you want to produce large volumes, you need to do it. You need to have many more print heads if you want to do multi-materials, for example, and you have to have a lot more control over your settings. You have to have a lot more control over the inkjet drops that are coming out of it. You need to control that because, for example, if you're printing a line of metallic material, conductive material, and you have one drop that is not spotting or jetting as it should, then you get a hole in your conductive track, and that will then ruin the electrical performance. So there's a lot more. There's a lot more control and a lot more, that has to be done if you want to do this for industry, for electronics. Also, something about the curing and sintering technology. So now the one thing is you have a conductive path on top of your. You can deposit some some conductive. Usually an ink it has nanoparticles in it, or particles, conductive polymers, or pigment in it, and then you need to be able to in order to get that functional, you need to actually sinter it or cure it. So one thing is to dissolve any solvents that are in there, but also you need to melt the particles together to get an improved conductivity. There's a lot of ways to do this: convection heat, NIR sintering, laser sintering, and something called photonic sintering. NIR is a near field infrared radiation. Laser is, of course, later. The most conventional is just heating on a hot plate or something like that. It's very normal, but it's it's very time consuming. It can take maybe 30 minutes to do the convection heating. NIR sintering is on the orders of minutes. Laser and photonic can be much lower in time, but require specialized equipment, more expensive equipment. Just to show you that what is the something about photonic sintering, which I think is a very, very promising and technology, up-and-coming technology, which is actually already commercial available production technologies. Novacentrix, for example, what I'm showing here has a photonic curing systems that you can buy and implement in your production lines quite readily. So the idea is that you have a high-powered xenon pulse light source, then you flash on top of your printed structures, and that flashing is then superheating absorbing in the ink, and not the substrate. That means you're only getting heating in the ink itself, maybe hundreds up to 500-600 degrees Celsius in some cases. And then, of course, the substrate is actually almost room temperature. So that means you can work with low temperature substrates like plastics and stuff like that with this system. It does it in a matter of milliseconds, and then that means that you can imagine that you can actually anneal and cure faster than you can actually print the structures themselves. So that's actually very nice compared to the convection heating, which is normally used in production technologies today. It takes minutes, if not tens of minutes, to cure. So going from tens of minutes to milliseconds is actually a huge advantage. So now we have a few questions I can see that have popped up during the first part of the talk. So I'll try to address those questions. First, Thomas asks, can you make a circuit using this technique, or is it different, or is the difference in conductivity too low? Actually, yes, you can make there's actually a lot of RFID tags and all these are circuits, and they're also all being produced using this technique, printing techniques. So it's a very standard technique for that. Depending on the ink you're using, and I'll talk about that in the next part of the talk, you can get conductivities that are maybe 5 to 10 or 10 to 15 times the bulk of silver, for example, if you're using a silver technology. However, this is okay because you can just add, you just increase the thickness, and then you can get the sheet resistances that you need. But there are also other inks that actually have performance very, very, very close to bulk properties, so deposited properties. So this is becoming a bit easier and better. The next question is from Jan Jacobs. What is the highest aspect ratio, height versus width, you can achieve with printing? I would say in a single layer of printing, even if it's screen print or inkjet, the aspect ratio is not very high. However, what you can do is then print layers. So you can print 1, 2 multi-layers. So as long as your alignment is very, very good, and in a lot of systems it is actually very, very good, you can actually then achieve very high aspect ratios. I've seen some examples with inkjet technology where you can have maybe 50 micrometer wide and maybe a millimeter high structures. So this is a very, very high aspect ratio. Anna Fast asks, can you use this technique with all base materials? Yeah, there actually is no, if you can make a material, if you can make particles, small particles out of any material, and you can perhaps formulate them into an ink. So right now there's a lot of different materials that are very standard actually. Metallic materials such as copper, silver, platinum, gold, aluminum, there are a lot of materials you can buy already. There are inks that you can buy on the market. Dielectric materials such as oxides, ceramics, polymers, of course, just plain polymers you can print using any of these techniques. So there's a wide range of materials you can use. I think it's and I would say if you want to try a new material, is if you can make it into a powder, a very fine powder, then we could probably formulate it and probably print it. Atref asks, is it possible to make a capacitor by printing two conductive layers in the same structure? Yes. You can already, for example, the application example I showed you with the conductive ink and the polymer, this could be very easy. You have you could just print the conductive ink and then the polymer and the conductive ink. No problem. This is a very standard way to do it. You can also print other electrical components, resistors, perhaps even inductors if you would like, and also different sensor layers. You know, temperature sensors, capacitive sensors. Exactly. I mean, there's a lot of different things, and yes, you can do this. Shoko Yamada asks, what about carbon-based materials? Carbon-based materials, yes, they are used, and there are products, there are inks that you can print. Depending on the application, I think I think carbon-based materials are used mainly for protective. For example, in EKG electrodes or ECG electrodes, usually using a silver for the conductive parts, and then you're coating them with carbon on top in order to get a nice, sort of a nice contact to the skin. That's not sort of toxic to the skin, because carbon is of course very compatible with biocompatible and not silver. So in that case, that's a good example of carbon. But using purely carbon for electronics is actually, I don't think, possible right now, not at all, and probably is going to be very challenging in the future, because carbon-based inks and carbon-based materials are not as conducting as, for example, silver or copper or other things. It's just the resistivities are orders of magnitude larger for carbon-based materials at the moment, and I don't see how that's going to be remedied in the future. Thomas is asking, what about the health risks? Yeah, I mean, if you're working with nanomaterials, there are definitely risks in the health. You need to really think about how you handle the nanopowders or micropowders. But if they're in the inks themselves, then that's actually, and it's in the dispersion. There is just then it's the solvents you're talking about, and the solvents, we all know the risks with solvents. They're very well documented. There's a lot of work being done on trying to figure out what are the health risks of working with powders and stuff like that, and so it's not well known at this point, but I think it's coming within the future, in the next few years, that there'll be more and more risk assessments when working with powders. Arnafast, is there any way to reuse the stirred materials in sintered materials? This is a very good question, and I'd say right now there is not that many methods to actually recycle printed materials, and that's actually a huge problem. Actually, so that means right now, if you're producing electronics, I think most of it, 60 to 70% of it, is disappearing. So that means that we need to be able to do that in the future. Otherwise, we're gonna all of a sudden we're not going to have any materials left. There's actually has been a few estimations that maybe we have 15 to 20 years of silver left that we can mine and then use for electronics. So it's something we have to think about, definitely. Okay, I think there's no more questions right now, so I think we'll have to move on to the next part of the talk, and that is about the nanomaterials and the conductive inks. So right now, I just want to say, so if you want, what is a conductive ink? Well, you have three main constituents. You need some conductive pigment. I give you two examples here. There's some nanoparticles on the top, and there's micro silver flakes on the bottom. So I would call them a nano ink and a micro ink. Then you need, of course, some solvents in order to make it, and you need some binder. The binder material is, of course, what gives its ability to adhere to a specific substrate, and the solvent is what is basically the carrier for the whole thing to make it printable. to give the liquid feature. And then, of course, by adding these three things together, then you get a nice ink that you can print. So what are the opportunities with Nano? So right now, if you look a little bit closely on this one, so if you have this micro silver, so these micro silver flakes, then in your ink, then when it dries, then they're going to just lay on top of each other and become very porous, and the actual conductivity is based on just physical touching mostly physical touching of the silver flakes on top of each other. In a nano ink, it's a little bit different because the nanoparticles are very, very small, and that means that they like to pack together into a nice ordered structure, and that means that in the end you get a film which is much more dense, and in that case much more conducting. Here's some examples of what it looks like in real life. These are sort of cross-sectional images of a micro silver ink and a nano silver ink on the left and the right side respectively. You can see on the left side you have a lot of the dark part is the binder system, so you can see it's just a very porous structure and not going to be very conductive. If you look at the electrical performance, this is some based on literature I've sort of pulled out. So there's of course a lot of literature, and every ink is a little bit different. So, but just to give you some general indications of how this is looking. So in the best cases, so on the left hand side you see the micro silver ink resistivities as a function of different curing and sintering procedures. In the best case, I would say that you get the lowest resistivity is around 20 microohm centimeter, which is approximately 10 to 15 times the bulk value of silver itself. So it's quite a large difference because of this large porosity and etc. And if you really want, and then of course that's achieved at 850 degrees Celsius. You had to go really high temperature. For the lower temperature curing, then you have orders of magnitude larger, so it's not very good. In the nano silver, there's two things that are happening. Number one, you can actually achieve much lower resistivities, down to around 2 to 3 microohm centimeter, compared to 20, sorry. Plus, you can do this at very lower temperatures, and this is because the nanoparticles, because of the large surface area, they will sinter at much lower temperatures than the microsilver particles. So what is this saying all in all? It's saying that if you use the nano materials instead of micromaterials, then you can actually save a lot of material, because the electrical performance is going to be at least 7 to 10 times better, depending of course on the substrate and the annealing temperature and the annealing parameters, etc. So that is a huge savings. Then you're asking probably, why aren't we using this standard nanoparticles all the time? And I'll just say that usually we do not. Most of the commercial products you see in day, RFID tags, solar cell electrodes, etc., are using microsilver inks. And yeah, the main reason, there are some challenges with nano. The first challenge is the production. Right now the production of microsilver is well established. You can do it in very, very large volumes, and you can get this silver micro powder extremely easily. So basically what you do is you take bulk silver and then you just grind it into a powder. So it's very simple, very cheap. The price of a micro powder, these microflakes, is actually almost the same price as bulk silver. So you really can't get any cheaper than it already is. On the other hand, if you want to make nanoparticles, you usually do this using a chemical synthesis, a wet chemical synthesis. That means you need chemical precursors, metallic precursors, then you reduce them, you need reducing agents, etc. That means the raw materials you need are more, and they're more expensive because they're not raw materials, they're actually processed materials. Right now you can only do this in small and medium volumes, so there's not that many places, or if at all any, that are doing it in its largest part volumes as the micro materials. And it is actually difficult to upscale. A lot of people are making hundreds of grams or something like that, but you can't really take a process from making a 100-gram or a 50-gram batch up to kilos, because things the kinematics of the chemical process, for example, temperature, mixing, and all that change when you scale up in volume. So there's a huge challenge in trying to produce nanomaterials in a cheap and efficient way. If we look at this in the price, so right now I would say this is the price per performance on the y-axis as a function of the price of Nano Silver. And then I put the sort of micro silver is a base because it's not going to get any cheaper. It's more or less it's been around for many years, so this is the way it is. So if we want the nanoparticles to become cost effective compared to the micro silver particles, then we need to have to push down the price below around 3,000 euros per kilo. Right now, I would say that the prices are more in the range of 8 to 10,000. So it's much more expensive and it's not yet cost effective. But this is something that people are working on, and also what we are working on here at DTI. A little bit about maybe some alternative materials, because silver is not the only material that can be used. It is the most well-known and most used material because of the, number one, the bulk resistivity is very low, one of the lowest of all the materials, and plus the oxide of silver is also conducting. So it's easy to formulate into inks, and there's a lot of know-how in that. What you could do and what people are actually looking into is alternative materials. For example, copper is a very interesting material, mostly because of the price. If you look at the price and availability, there's a much more copper that we can mine and we can actually use than there are silver, and that also means that the actual price of copper is about 100 times less than silver. So that actually right there means that if you can make a silver-based product, ink, then it will inherently have a much lower price. And even the resistivity is actually not that much different. So there's a huge opportunity of using copper. The big challenge of copper, of course, is that copper oxide, which is copper oxidizes quite readily, and copper oxide is not conducting. That means if you have copper oxide in your copper, then it's not going to conduct any electricity at all. People are actually looking into this. Actually, there is some products already on the market. Novacentrix actually sells a copper oxide ink, and the idea is that they make a copper oxide ink, and then you can print copper oxide, and then you can use their photonic sintering, so that with the high energy sintering that they have as well, they can actually reduce the copper oxide to pure copper. And then you can actually have copper tracks onto paper or any other plastics or whatever substrates, and it works quite well. So this is a commercial product that is the thing is that you cannot. You need to have the photonic sintering, which is a very expensive technique. The last thing I want to talk about with the challenges is that what ink producers would like to have is just to sort of basically just take they have binder and solvent systems for large scale production of their inks and pastes. What they would like to do is just to sort of replace the silver, the micro silver they're using with something better, and this means that you need and another thing with the nanoparticles is that you do actually need coatings on top of the particles to make them stable, and also to preserve them. For example, if you want copper particles, you need to coat them in order to so they don't oxidize. So that means, and if you look at that in terms of the size of the particles, it's very it's sort of intuitive that the smaller the particle, and then that means the larger the surface area, and that means the more coating, the more organic content you need. So that means, so this type of trying to, you need to envision entirely new formulation schemes, binder systems, solvents for actually working with nanomaterials compared to the current micromaterials. This is something also that is a barrier for having nanomaterials into conductive or printed inks and pastes. So just some conclusions on what we've been talking about already. Number one, many new application areas are on the rise and new markets are emerging every day. So this is something that's very exciting, and we can see that there's a lot of people that are getting interested in printed electronics and what we can do with printed electronics. Printing technology is very mature. I would say the main challenge is not in the printing technologies, but in the development of functional and stable nanomaterials and nano inks. Potentially, you can get much better electrical performance using nanomaterials compared to micromaterials. I showed you some examples of that. However, the production of the nanomaterials is still lacking, and that has to be addressed in order to get these materials on the market into inks and into components. So this, in all, new nanomaterials and protective technologies are needed in order to get this to a more state. And this is something that DTI, of course, is working quite a lot on. Yeah, so then there's some questions. It seems that there is not any more questions or any questions at this point, so I will just go to the last part of the talk, which is what are we doing at DTI? So first of all, I want to say that DTI is a self-owned company working with research and innovation of different technologies that are close to the market together with industrial players. So we're trying to figure out what is needed for the industry, and we're doing very industrial or commercially focused R&D. What we are doing at the Nano Production and Microanalysis Center, where I am working, we have focused on micro and nanotechnologies. We are working a lot with nanomaterials. And this is for nano inks and dispersions, which I've been talking about today. We are also working with digital manufacturing based on inkjet technologies. We have some very good infrastructure, some tools for that, which I'll show you in a bit. We are working with nano catalyst systems as well, also based on nanomaterials, so a lot of different catalytic systems. And in order to tie all that together, we're working a lot with nanomaterial reactors, actually looking at how to produce these nanomaterials in a cost-efficient and scalable manner. And that what we're doing in that case is not using batch methods which are used today, but we're using flow synthesis methods. So in this case, you can sort of, in a flow system, mix your reagents very efficiently, control the temperature, control the pressure, control the kinetics of the process, and then you can actually scale that up by having higher and higher flows and volumes that are produced. On top of that, we have a lot of work on characterization, coatings, and we're also working a little bit with energy systems, fuel cells, microfuel cells, battery systems as well. So this is a little bit of what we're doing. Within printed electronics, we are actually trying to sort of service the entire value chain. We actually do some fundamental studies together with universities, and this is very, very university driven. But then we are trying to take these results and sort of use them into the more commercial side of aspect of the materials and the printed components. So we do a lot of fundamental studies on how things are synthesized, how things work on a chemical level, on an atomic level. Then we try to use that to produce very controlled nanomaterials and also do that in large volumes. Then we take this and we make ink formulations, and we then can do process development and also pilot production of components. And we usually do this in a very application-driven manner, so having good collaboration with end users. The products that we have now, the nanomaterials we've been working a lot on, not strange enough, is the main one is nano copper. So we have a lot of different nano coppers, and these are also always capped with organic materials. So we can make nano copper, which is capped. We can actually formulate it into inks and pastes, and we can actually print with these materials. An example of this is here. This is actually a screen printable ink that we made together with a company, Italian company called Schmidt some years ago. It was a 70% nano copper ink. They made some screen printing tests, and we evaluated the conductivity, the electrical performance of that. The powder itself was actually very, very stable, also in this dispersion, several months without oxidation. So we actually are able to protect and make stable the particles. And I think the results in this case were pretty promising. We got, I think, values down to 5 to 10 times the bulk values of copper at around 400 degrees centigrade. And this is just using a convection, a hot plate. So nothing fancy, nothing too fancy. We also make silver because a lot of customers that we work with are working with micro silver, so they want to have nano silver and try to see. So we're doing a lot of development in nano silver to try to meet the demands of the industry. So we have a lot of different types of nano silver. And then, of course, on the other hand, we're also working a lot with prototyping. And so in this case, we are focused more not on analog printing, but we know people that do that, but we're focused on digital printing. So we just have invested in a digital inkjet and aerosol jet printing system, which basically in this case we have we have the possibility to print with 2 or 3 different materials at the same time. And we have an NIR and a UV curing system as well. So, and this is in the same system. That means we can print, cure, print with another material, cure, etc., all automated and all in the same system. So making 2D electronics, 3D stacked electronics, high aspect ratio things, we can do all that with this system. The cool thing about this system is that we can actually transfer all the processes to a more industrial printing system, which is done not by us, but of course by a Zero Drops, which is owned by the MGI Group, which actually make production tools for industry. So we're not just going to do prototyping. In the end, we can actually transfer that to a industrial production line. Just a little bit about the inks and the materials we've been working with so far in our prototyping. We've been working a lot with silver, copper, gold, platinum, polymers as well. We've been working on paper substrates. This is very interesting and actually very easy. Paper is actually a very nice material to work with. Plastics such as Captain and PET. Rigid substrates like aluminum, glass, even metals if you want it. We can do multi-materials right now. I mean, 2 or 3 materials that we can print at the same time, and we have as I said, the NIR and the UV curing systems. So, what can DTI do for you? So, just to sum it up, we can develop and produce tailored nanomaterials. We can do this in moderate to pilot scale production right now, and we can also help you if you really want to scale up that production. We can help you if you want to use some of the technologies we are using, the flow synthesis technologies. We can do process development and pilot production using inkjet technologies with this F-series production or pilot production system I just showed you. We can also find funding opportunities. So if you're a small and medium-sized enterprise, then that needs some help getting funding, we can do both national and international funding schemes. We have a lot of expertise. We actually do run research projects, horizon projects, etc. So we know a lot about that. Last but not least, we can actually, if we don't have the expertise that you want in terms of the printing technologies, because we're working mainly with digital printing, we do have a lot of connections. We do have a lot of collaborators with a lot of large RTOs in Europe, and we can then connect you to the right partner. So with that, I want to say thank you very much for listening. If you have any questions or you have any want to discuss any topics a little bit more in detail, please contact me. Here's my contact information. And otherwise, I want to say thank you for a very nice for listening, and I'll talk to you hopefully soon.